Hi everyone, welcome. So we're going to be onboarding on our journey for the class EE274 on data compression, theory and applications. And today it's all going to be about introduction and logistics, and then we'll just deep dive into the material towards the second half. So this is your course staff. We have Professor Tsachy Weissman sitting right there in the cool jacket. We have Shubham, who is also there, and he'll be taking the second half of today's lecture. I am Pulkit, and I'll also be part lecturer. And then finally, we have our awesome TA sitting there, so for any class-related material. We also have Kedar, who was the instructor from last year, who will be helping us from the sidelines. So you have another extra resource at your disposal. Okay, so let's just dive in. So this is like a curve which you might encounter at some point in your life, okay? The y-axis here is the data volume in zettabytes, and the x-axis is the year. So this is like the volume of data which has been created and replicated worldwide, okay? And it has a trend which is like, okay, it's exponentially increasing. But like, and this kind of curve kind of shows up in all sorts of applications. But like, what does these numbers really mean? Like, right? Like, what do they reflect? More precisely, like, what exactly is a zettabyte? Like, why should I care? Right? So let's try to get some sense of these numbers. Okay. So let's start with a megabyte. So megabyte really is 6 zeros behind that one. And it's roughly the space which is occupied by a lossless image in your smartphone. So this is the image of my cousin's dog, Ace, and the unfiltered version of it was taking approximately a megabyte on my phone. Okay? Continuing, as you add 3 more zeros behind it, you get a gigabyte, which is approximately the space which is occupied by a typical 4K video of a few minutes duration. And this was supposed to stream automatically from YouTube, but it was basically a video clip of your favorite anime. Okay? Continuing, if you add 3 more zeros behind it, now we start talking about terabytes. Okay? And this is something which I'm sure at some point you might have encountered when you went on to buy an electronic device from your favorite manufacturer. This is what that manufacturer kind of charges you for each extra terabyte storage. Okay? And you need that extra terabyte storage year after year, right, to store all those photos and videos which we just talked about. Okay? So at this point, with the, I guess, 12 zeros behind, we are already at the typical storage which is available on your laptops as of now. Okay? Let's continue. Add another 3 zeros. And what we get is actually a petabyte. And at this scale, we are now talking about the databases which are stored by like really even medium scale companies as of today's standards. It's actually the de facto cloud storage unit. So if you have ever heard of AWS S3, Google Storage, Azure, like all of these are cloud storage services where you can store your data. And when you talk about like how much data is being stored by these companies, you would typically talk in units of like petabytes. And again, a petabyte, like at each of these steps, we have been adding 3 orders of magnitude behind what we have been seeing before. Okay? In fact, like a cool fact, like Meta was roughly generating more than a petabyte of data to be ingested every day. Like every day. Okay? And so at this scale, basically what you're talking about is millions of dollars of management. If you are a business person from a company managing this data, or if you are a team at AWS S3 or GCS, you are like by managing petabytes of data, you're talking about millions of dollars of data in management under your control. Okay. So far, so good. Let's add another 3 zeros. Because why not? So now we are at 1, 2, 3, 4, 5, 6. 6 times 3 zeros behind the 1 of the bytes which we were talking about. And what you get is an exabyte. And this is roughly the estimate of data which is being transferred over the internet daily. Every day. This is the amount of bytes you are like sending to and back. Okay? And this finally leads us to what this number zettabyte really is. Right? 1 zettabyte is actually 3 orders of magnitude over what I just talked about, the last thing. So I want to wait a second and I want you guys to really appreciate these are like 21 zeros. We started with just 6 zeros behind one of your photos. It's not multiplied by 2. It's multiplied by 10 raised to 15 from that single photo which you are very carefree to capture on your phone, right? And this zettabyte is what's being shown on this curve. So when you went on from, let's say, 2 zettabyte around 2010 to something like 64 zettabytes, it's actually 62 of 21 zeros of data added in the world. Okay? So clearly managing this much amount of data is an issue. Like data is growing at an exponential scale, and this is a serious problem in all applications. Right? You have to somehow manage this data. You have to somehow understand this data. You have to use this data to drive your business, or you have to use this data to really come up with the cool machine learning applications if that's what you care about. Okay? So this clearly says that like there is a need. Like if this continues, like we won't just have enough space to store data for ourselves, right? So you have to worry about the storage at this point. Okay. But interestingly, it's not just about data at rest. It's not about just, okay, I collect this data, I store it at one place, and life is great if I can do that. It's also about the data in motion. Once you store this data, you will use it for 1,000 different applications, for analytics, for just transferring data to your friends, so on and so forth. Right? And that's also a very big issue. Like you have to move this data around. So this is like an estimate of like the proportion of internet data traffic around, I think, 2021. And here, what you see interestingly is videos are taking roughly 50% of your internet data traffic daily. And this is a serious issue. How can I convince you that? Back during COVID, Netflix got a technical request, like legal request from EU to reduce its bandwidth, because they were just not able to support it. They were not able to support the increase in data traffic around their networks. So Netflix was basically asked to either reduce the quality or improve their compression algorithms, improve the compression which they provide. Right? And again, like these are just like some conservative numbers of like what you are really streaming when you are watching your favorite show, like how much data you are consuming without even thinking twice about it. Right? So these numbers, if you just look at them, like a high definition Netflix stream can use as much as 3 GB of data each hour. Okay? These numbers and the world which we live in is unprecedented, and it's on an exponential growth scale with respect to the data. Okay? Great. But the interesting part, as I said about videos and Netflix, right? But it's not just about videos. It's not about any single kind of data. Data compression shows up and is of value wherever you collect data and whatever kind of data you are collecting. So things like text, log files, code, even like if you ever use GitHub, and you do a git pull, this is like a standard message which comes up. So this is, for example, an instance of when I was updating the website for the course. And very interestingly here it says something like compressing objects, right? So if you have never ever actually looked at it carefully, even GitHub, every time you are doing a pull, push, any of those things, you have to compress. Otherwise you can't really do a version management. You just can't creating copies at every single change which you are making and committing to your favorite repo. Okay? So this is like working in the background. But not only that, there are like genomic data, emails, all your Google searches, tweets, images, videos, things like EEG, which is like electroencephalogram, like sensor data. Like if you think about like the biomedical applications, the amount of data you are collecting is immense. And again, many times it's not even possible to transmit this data, collect this data, let alone like do any sort of analysis on top of it. Like neural recordings, your multiverse, and not even that, even LLMs and ML models. So if you care about machine learning, like there is a big push for there is a deeper connection between compression and machine learning models. And there is like bidirectional communication, in the sense like people have been using machine learning to improve compression. But not only that, compression has been an integral part to understand what's happening in machine learning. So if you are aware what's happening of maybe, I don't know, llama and so on and so forth, you would also know there are all these sorts of quantized models. Like, why do you need these quantized models? Why is everyone after them? Because unless you do that, you can't run any of these things on your favorite devices. Okay? So what I really want to highlight here is like it's omnipresent. No matter what's your application area, maybe you're a bioengineer, maybe you don't care, you're just a software engineer and wants to have the most efficient version management for your softwares, or you're just a machine learning engineer, right? No matter what you do, you will see compression at play at some point during your lifetime. Okay, even more interestingly, your compression, it's filled with trade-offs. It's not really like when GitHub says like, okay, compressed. There were a lot of design decisions which were made in the background. And what we'll teach you in this class is also to understand like how to make these design decisions, right? It's not just about taking a file, right-clicking, compress, and be done, right? It's always about like the trade-offs given your applications, what you really want to achieve. And this is like a curve which we'll see a lot in the, or like variants of it, a lot in the second half, and Tsachy will cover its theoretical aspects too. But basically what I'm showing here on the x-axis is size, and on the y-axis is error. And for those of you who are aware, it's like rate distortion curve, if you would have heard of it at some point in your life. And the basic idea is this, that when you have higher size, you can get away with smaller errors in your files, right? And as you keep decreasing your size, you will have higher and higher errors, right? And this kind of leads to some very interesting trade-offs. And maybe let's get into some of them. Let's try if this works or not. Okay. So now, hello, yeah. Now I'm going to play some audio files for you, and let's just see what you guys feel about them, okay? So this is the first audio file. Okay. I don't know, maybe some of you recognize what was being played. Maybe not. But this is like that audio file at roughly 5 MB. Okay, and that's maybe this point. Let's reduce the size and rehear what this file sounds like. Okay. Any thoughts? Like, was it good, bad, don't care? You have some thoughts? Oh, shouldn't play. Okay. Anyone? Yeah? You felt the quality went down? Oh, a little bit? Okay. But was it okay? Like in the sense, would you still... Oh, okay. Actually, any other thoughts from the class? So, right? Felt that the quality went down. Anyone else? Any thoughts? Couldn't notice. Sorry, what's your name? Okay. So, here said that he couldn't notice much difference. Great. So we have some difference in opinion here already. And we reduce the file size to something like half. Okay. Let's go down a little further and see how that sounds like. Okay. What about now? Bit worse, but you might still live with it. Okay, that's fair to say. Anyone else, any thoughts? Yeah?
The frequencies are distorted. Like the last one was much more shrill and like unpleasant.
Okay, sorry, what's your name? So here observed that the frequencies went down, and he found that the last one was like a bit shrill, and just like something was off. And again, like the point which I want to highlight is that at this point, you have compressed the file. And even in this classroom, which is really small, the scale of world, we have some difference in opinion, right? Maybe said he can live with 2.5 MB, he doesn't care, is not cool with that. Like, even going from 5.3 to 2.5 MB is like, this is my favorite song, I can't hear it like that, right? And when we went down even further, there was again some more disagreements, right? Like some of you might be okay, some of you weren't. And these are the real trade-offs which you face in real world, right? Like you have to take a call. Like if your phone just have, I don't know, a megabyte space left, you can't do anything. You have to go down to that size. But something interesting to note was even at, I don't know, we reduce it by roughly 5x, the audio quality sounds still okay. Like if that was the space which you have left in your phone, you might still want to keep it. But let's say if you're streaming it over the Stanford network, you wouldn't like to do that. You would like to hear the best quality, right? Okay. So this was just an example of the audio. Continuing, we can look at the same example for images. So this is like a popular character out there. Just an image of the character. If you don't know, don't worry. If you know, hope you like the show. So it's this is the image stored at 585 kilobytes. Again, let's reduce the size further, and this is at 280 kilobytes. For me, I am okay, right? Let's reduce the size further, and now this is the same thing at 13 kilobytes. Okay, we have reduced the file size by, I don't know, around like 500x, right? And there are two comments, like more or less, I think this is okay. This still captures like the big part of this images, right? Like you can still make out the character. But if you are a connoisseur, or if you really like to watch a lot of movies and like whatnot, maybe you observe that there were like some distortions which started showing up, like ringing artifacts right around here, okay? And during the class, we'll get into such details. Why these things happen, what are the compressors being used, when you can throw away stuff without introducing a lot of distortions. And this is basically the job of all the big businesses. Like Netflix optimizes its stream so that you can get the best quality, or your favorite streaming provider, right? Same with Spotify. Like if you look at Spotify settings, you would see like whether you want the highest quality or the best data saving mode. This is the curve along which they are basically playing. So hopefully, by the end of the class, you can appreciate all these things better technically and be able to understand these trade-offs more intricately. Okay, so I'll wait. Any questions so far? Cool. And so, okay, so this is really the punchline, right? And I'm quoting Tsachy, who's just sitting right behind, because this is where I heard it first from, and I really think this line kind of summarizes the data compression, which is, it's basically the succinct representation of information. Okay, so you are okay to throw away stuff as long as you don't throw away information, or you try to keep basically whatever message being communicated through whichever medium as close as possible to the original one. And like we have been saying, like, why do we care about compression? I think I'll go through this like fast because I did show you guys some examples of why you might care about the compression. But basic points have remained the same. So like storage is costly, and like we are generating exponentially exabytes more data, right? More so, it is really purest form of information processing. Compression intricately is related to your signal denoising in a way. You are basically trying to keep the most useful part of the information in whatever thing you are outputting out of this compression, right? And in same way, it's equivalent to communication without noise, right? So when you're communicating, maybe you are adding some noise, you are spending some storage to actually, or some bits to actually spend on those noise. And what compression tries to do is extract the relevant information out of it. Okay? So you also have these compressed representations, which might be very easy to transmit and search on, because now you have thrown away the fluff and kept really the information part of the things. And it can even simplify implementations. For example, if you are working on just the compressed representation instead of like the whole big data, you may not be able to move that whole big data, versus if you're working with a smaller part of it, maybe you can do something about it, right? More so, it has a very fundamental relation to the data modeling, prediction, and even like your favorite ML, so as to say, right? And this is a point which we'll try to drive home at some point, that basically a good compressor is a good predictor, and vice versa. If you basically somehow are able to come up with a good predictor, you can use it for compression, sans some conditions, which we'll talk about, and so on and so forth, right? So it's very fundamentally linked to what you are able to predict. And finally, it is really a very critical building block in today's, I would say, any scalable and efficient system. Okay? In fact, my first foray into compression wasn't even through the standard compression thing. I was trying to build an application for brain-machine interfaces, and there was absolutely no way I could have collected that data and transmitted it. Like, it was just impossible. I was working on some eye prosthesis, and I would have burned the eye, like way before I would have been able to collect the data I would need. Okay? So what I'm really trying to highlight is, no matter what application you are into, at some point you might run into compression just as a necessity. Or we have actually sitting in the class, and like in her case, like she used compression as a tool for her application. And that's another way where like you might come up with some of the tools. We'll talk in this, you might use some of the tools which we might come in this class in very interesting ways in your application. And that all stems back to all of these things, that essentially it has very deep connection to prediction. It is basically the purest form of information processing. So compression is basically what I want to highlight. It's way beyond, again, right click, compress, zip, done. It is very interesting. In fact, it is so interesting. Actually, let me pause here. Any questions so far? Okay. Yeah, so compression is super interesting no matter what your interests are. Okay? So what I want to highlight is that there is something for everyone who's sitting here. You love theory. You really like to understand the world in mathematical formulations. Compression has very deep connections to information theory. And here it's Claude Shannon, who's like the father of information theory. Okay? For example, I started this presentation with exabytes, megabyte, kilo, like whatever, terabytes, so on and so forth. And all of you were like, yeah, we understand. Very cool, right? Sure. So we are in a digital information age. Everybody know what bits are, what bytes are, right? But basically it has a very fundamental connection to whatever we have been doing. It has fundamental connection to information. And it's not coincidental or arbitrary that we are talking in terms of bytes. And in fact, we'll cover the basics in this course next week. Most likely you'll start seeing the exact bits coming up. But if you're more interested, I would encourage you guys to take EE276, which is a specific information theory course, again, taught by Tsachy. Okay. Another interesting question. So take your favorite compressor, I don't know, whichever one you want to pick. Input it a file. Like, I don't know if you have ever thought of it, but why can't I just keep applying it in a loop? Like, whatever output I get out of, I don't know, zip, let me zip it again, zip it again, zip it again. Why am I not able to get to 0 bytes? Like, where am I taking any space? Okay. So actually, very interestingly, apart from the implementation inefficiencies, no matter what you do, there is like a fundamental limit to where you can compress things. And it's very well understood mathematically. And that's where like the entropy term gets introduced, and we'll explain it to you. So funny, if somebody comes to you with their $1 billion pitch and they say we can reduce all the file sizes by, I don't know, 99.999999%, you can turn it down very politely after taking this course. Like, don't entertain. Okay. Another fundamental question is like, for example, which we saw in the audios and videos case, images case, which is, how much can I compress if I'm okay to lose some information? Right? For example, in that image case, we went from 515 kilobytes to 13 kilobytes, right? And we got some quality. Was this the best thing I could have ever done? Could I have done something better? And again, there is like a very interesting, to the core, beautiful mathematical theory for it, which is called rate distortion theory, and you'll understand that there are like fundamental limitations to what you can do there again. Okay? So if you are into theory, there are some very interesting questions which involve compression. Okay. Maybe some of you are from CS here, and you don't care about theory as much, but you get very excited with algorithms, right? Like you want to just, like, okay, there are like extremely elegant algorithms which are involved in compression, right? And we'll introduce some of them in the class. So here's a picture of Limple and Zip, which is the LZ, and hopefully by the end of this class you will be like, you will know. So I'm throwing lots of acronyms here at the end, but the hope is by the end of this class you will be familiar with them, you'll be conversant with them, you'll be able to talk with your peers and others who work in compression about them and be able to understand these things technically. So for example, there is like existence of universal lossless data compression algorithms, which is like the reason for popularity of all these LZ based schemes. For example, gzip is an LZ based scheme. Okay. Even more so, there is like all this usage of transforms in multimedia compression, like KLT, FFT, DCT, and you'll understand why these algorithms and to be able to do these things efficiently is extremely important for compression. And finally, like again, very interestingly, like there are questions like how are numeral systems, like 2 times 10 plus 2 equals to 22, how is this related to compression? And you might find it very surprising, but it is. And you'll learn in this class how. And finally, if you are someone who's like even like a true engineer, who goes right down the assembly code or writes the most efficient software code, you don't really care about the algorithm, you want to optimize to the dot, there are some extremely clever implementations involved in compression. Because as you might imagine, like nobody has the time to wait for your video file to decode in a day if you want to watch your favorite Netflix stream or whatever it is, right? Just absolutely no one has time. And so there are some very extreme clever implementations which people have come through in this. So for example, like I'm gonna just combine this in a single go, which is like, can we cache computations? Very simple questions, right? But if you are someone who has done computer architecture or hardware, like you'll be surprised to know there are like specific hardware implementations in your laptops right now, just for being able to run a video decoder, without which your videos won't run real time on your favorite browser. So people have not only optimized software, they have went on and worked at the level of instruction set architectures to optimize the compression algorithms and theory which just preceded. Okay, this is a fun one. I don't know if you guys have noticed, but if you are trying to go back and forth on YouTube, Netflix, Prime, whatever it is, there is like some smallest delta at which you can go back and forth. Maybe it's 5 seconds, maybe it's 1 second, 2 seconds, depends. Right? But notice, like try it after you go home today. Like YouTube, you maybe will have to check. I think it's 5. No, it's 1, I think. I don't know, but some point it used to be 5. And if you go back and forth, you can't go back and forth in units smaller than them. Okay? And that's also very interesting because it comes around from a clever implementation for you being able to stream videos real time. If you don't do that, if you try to give a millisecond level stream, like millisecond level seek for the videos, you won't be able to decompress it real time. And then you'll start seeing the annoying bar, the annoying circle, which everyone hates. Okay, so that's actually a side phenomena which is coming from a clever implementation. And there, basically, you have something called frame groups, IPB frames, which is again something which we'll touch in this lecture at some point. And finally, there are also some interesting data structures which shows up, like suffix trees and BWT transform. In fact, there were like data structures which were designed for compression and now are mainstream in certain places like genomics. Okay? And so really the takeaway of all of these examples is that no matter what you like, there is something fun for you in the field of compression. And in this class, like how this class I would say differs from the other offerings, even at Stanford, is that we'll try to give you a flavor of all these three and like kind of packed in a quarters framework. Yeah. So in particular, the first half of the course, so now we'll get a little bit into the course. The first half of the course would deal with lossless compression, which is like if you don't lose any information. And the second half would deal with the lossy compression, which is like, okay, I'm okay to lose some information. What's the best I can do now? And throughout the course, we'll keep showing you workings of various tools and code snippets. So there'll be a mix of, we'll also show you some theory, some proofs, but we'll also show you like lots of tools and code snippets. So hopefully it will be fun for everyone and you'll try to appreciate the same material from different angles. So this is just course outline. It's also available on the website, but let me just go through real quick. So on lossless compression side, we'll talk about entropy and its fundamental role in compression, like we have been saying, for the, I think till week 2 roughly. And then we'll start getting into the lossless compressors right from week 3 of the class. And there we'll study like lots of compressors like Huffman, arithmetic coding, asymmetric numeral systems, your LZ, or hopefully by the end of it all, you would have a deeper understanding of how gzip works or how you can do lossless compression much better for whatever application you have. We'll also talk about how you can handle correlated sources, so things like adaptive arithmetic coding. Okay. And this is going to be roughly till lecture 10, so first half of the class. And then the second half of the class will be around lossy compression, where, like I said, I've been saying for some time, we'll talk about rate distortion theory and mutual information. We'll talk about quantization. We'll talk about transform coding, like all these different transforms. Why do they show up? Why do they matter? And then we'll have basically a very deep dive into images. I think roughly 2.5, 3 lectures almost, where we'll talk about image compression because a lot of these principles kind of tie together there. In particular, we'll talk a little bit about how JPEG works, BPG works, as well as how ML in particular has been used to improve compressors. So like the new age compressors, people have been trying to incorporate all these new ML findings. So we'll have a dedicated lecture on that, on like how you can do learned compression. And finally, we'll kind of wrap it up with like video compression, because as I think I've been highlighting, video is a really big part of your streaming pipeline and some role of like human perception and lossy compression. And the hope is by the end of this, what I'm showing here on the right is just like there's this tool which gives you properties of a compressed file, in this case, a JPEG file on my laptop. And there are a bunch of things. And maybe some of you are familiar with some of them, maybe all of them, maybe not. For example, things like what does this encoding process means, baseline DCT, Huffman coding. What does this YCDR sampling means? What does this color space mean, right? Things like this. And hopefully by the end of all of this, you would be able to appreciate these things and understand and make through. Okay. And then finally, it's a rich field. We are only going to touch like the tip of the iceberg, but there are like a bunch of interesting extensions, which we would encourage you guys to play with during the course project. So I don't know, like I've been saying, so if some of you are really proficient in ML and that's what you want to do, you'll come talk to us and we'll try to frame a very concrete problem for you around, let's say, compression and neural nets. Maybe it's not just about using ML, but also like you have this big neural nets, how do you apply compression to them, right? So it's a two-direction thing. You can use ML for compression or you can compress your ML models to improve efficiency. So this is just like one of the examples. Or again, like I think I said at some point, like, so if some of you have architecture and hardware background, maybe the way you can dive deeper into this material is by picking up one of the algorithms and trying to implement it in your favorite favorite low-level language, right? So it's going to be up to you, but there are like lots of topics. And in particular, I'll say like, so we are going to organize something called Information Theory Forum, and it's going to have guest speakers, basically, like leaders in their field, also going to come and talk to us about various different topics. So think of them as like complementary aspect to the course. Okay, let me pause here for a couple minutes because after this we'll just go into the logistics of the class. Any questions so far? Any comments, thoughts? No? Cool. I think we should move on to the next part, and I think I would like to just end here, shamelessly stolen from Tsachy, but this is really the spirit of this course. Like, try to have fun. We are also here trying to have fun. We just find this material very nice and interesting, and we are always open to feedback, so do come talk to us if something is not working or something is working really well. We can do more of that. And so going ahead, now Shubham will take a deeper dive into the actual material. We'll start the actual material. And the first half again would be more on lossless, so we'll start our journey into the lossless compression.